Okay, welcome to the JUXT Season 3, Episode 3. And we're here today to talk about this concept of separating storage out from compute. This is something that we've been thinking a lot about in JUXT. It seems to be what our clients want more of as well, this idea of cheaper storage, but being able to do more with that data in a scalable way. But we're also looking at it from the prism of XTDB as well, this database product that we're building that gives you this temporal functionality. What we're aware of there is that we want a similar pattern where if we can separate out the storage and we separate out the processing, the compute from that, then we're going to have a much more scalable architecture. Of course, as we look across the industry, we're seeing things like data mesh and everyone really wondering how they can make use of these data lakes where data is so available, but it's stored in different ways and then to compute it in different ways to get the most out of it. There's a lot to dig into here. So we've got some good people on the panel today. We've got Håkan Råberg, who is the chief architect of XTDB. We've got Malcolm Sparks, who is the CTO of JUXT, and Jeremy Taylor, who is the offering manager of XTDB. So I think we should start really by asking, from a very simple perspective, what do we mean by separating out the storage from compute?
So my understanding, it's around fundamentally where the data is stored. So if the data is physically persisted where the compute is happening, as has been the case for many decades for performance reasons, that coupling is the opposite of separating storage and compute. So when you separate storage and compute, you're not really focused on the specifics of how it's done, but you want to remove that strict dependency between this is where the data physically resides, and these are the machines which can access it and query from it. And so a database which embraces separating storage and compute inherently has the capability to find and retrieve data, which may be on any other system or computer on the network. So it's really about that sort of isolation between these layers. You imagine the OSI hierarchy. That's that kind of deal. You want these very cleanly separated layers.
It's easy to think about what it's not, right? So we've been on client projects where there's like an Oracle database and that is responsible for storage, but it's also where you go to do any sort of processing. So I want to do a specific query, want to do some sort of analysis. I'd go to that Oracle database to execute that query for me. So the storage and compute are kind of happening in the same place. And then obviously what you rub up against is just how hard it is to scale that. And particularly when we're in a world where sometimes it's still on-prem. So you could have this installation of Oracle Enterprise and it's just incredibly expensive. And then there's people running around saying, hey, we just need a few more terabytes because some more data is going in. We need to do something slightly different with it. We need to get more RAM. And it just becomes a huge constraint and expense. So really people are wondering, well, how can I get similar kind of power or more power because there's more things I want to do with that data, but just not have such an expensive bottleneck or constraint in terms of how we get that data stored. Is that fair?
Yeah, I wanted to add a few things which I haven't talked about so far. We have all the positives, like you can start doing this, right? You get into a problem of discoverability, right? Like it's not strictly tied to mutability, but it helps. And this is usually what you see in these big data lakes and the kind of object stores, that you don't want like too much random churn and updates to these files that has once been produced by some system. You can also use this fact that you more or less have infinite storage. You essentially run new jobs, producing new data, which depend on other incoming files, etc. You need a way to kind of discover this data to even start being able to do this. Like just randomly storing things in the object store is possible, right? Like, and you then you have separated storage from compute, but you also in a way need to kind of marry them back together. Not the storage, but actual data itself needs to be in a timely manner appear to the compute nodes in an efficient way, which is actually something we are looking for. Like in a way, we're trying to solve all these problems at once. We're building the new version of XTDB. You could argue that we kind of bundling them together. And like one of the nice things about separating storage compute is actually also open, which is also one of the tenets of the new version of XTDB, that you can actually go straight to the object store, discover your data, and read it using normal tools like data science tools that you would have been using anyway when you're doing this kind of work. But we're also maintaining that kind of metadata where they're trying to figure out where it is and enabling it to timely arrive through different layers of caching. There's an element of caching here, right? They essentially separate storage compute is kind of just you treating the local disk as cache of an infinite disk which sits somewhere else, but most real processing would still happen locally in RAM or potentially cached on disk. So you wouldn't normally do the processing against these files directly. You need to kind of grab them locally.
Yeah, that makes sense. Like, I think as we're taking a step back and saying, of course, it's easy to say, well, let's not have the old model. Let's not have like a centralized database. In fact, you could imagine as a thought experiment, right? Let's say we've got this Oracle database and it's been used in this big institution, right? It's very expensive. And someone says, hey, we've got to separate storage from compute. So we all rock up with our sort of REPLs and our ETL tools, and we do a SQL query. I've actually tried to do this, by the way. It's very difficult to do against a large Oracle database. Got loads and loads of data. But anyway, as an aside, let's say we do a query and we pull that data out and then we put it into these CSV chunks and then we put them into an S3 store. Now, it kind of sounds obvious, but in a way, you've separated out the storage now. So now your compute can happen elsewhere, which is a great thing because you can now build these tools. They've got to suck in those chunks of data from those CSV chunks and do something with them. But I think what you're saying is, Håkan, there's a lot in there that you just said, and it's kind of like that's where the journey really starts, isn't it? Like if you want to have this kind of architecture, you have to have the discoverability story, which is what you just said, like which CSV chunks of this data in S3 do we actually need? Like, where are they? Like what contains what? And then, of course, as you said, like it's typically these chunks are immutable, right? So you have like an immutable sort of chunk of data in this object store. But then as you put it, well, then, you've got to avoid like the massive churn that comes in. And if people do want to go back in time and do updates, that's going to lead to more chunks. So you have to have some efficient process in managing this. I made a sort of flippant reference there to CSV, but there are technologies in this space. So is it worth potentially bringing us and our listeners up to speed on like, what is generally happening in this space?
So I think the general trend is to store optimally sized chunks. When you store your data, you don't want to store lots of tiny things or like one giant, huge thing, which is a big snapshot of everything. You need to get the granularity right. But the scale of that granularity ideally benefits as much as possible from things like compression and frequency of update versus network transfer times. You want these chunks of storage to be very flexible and to be able to move around this overall architecture nicely. And so various standards for how to encode information into these chunks exist. So things like Apache Parquet, sort of very successful columnar storage format, which is like an evolution, evolves from the pain that people have had with CSV files and having to have these sort of row-oriented batch processing jobs, which spend a lot of time just processing CSVs. It could converting them from their on-disk representation into something that could be processed in memory, whereas something like Parquet simplifies the storage of the files such that it can be read much faster in memory. And then at the extreme end, you have these in-memory formats like Apache Arrow, where actually the alignment of the data as it could be stored and how it can be accessed from multiple cores in a machine is like one-to-one. So what we're interested in the XT team is using Apache Arrow as the foundation for separating storage and compute, which is a relatively novel thing because most people who have deeply invested in these open standards are looking at Parquet, but Parquet has limitations that we are not able to overcome, like the ability to store like multiple different types of values in the same column in a schemaless way. You don't want to have to decide up front what values can be combined. So yeah, there's a spectrum of formats that are available, and Apache Arrow in particular is interesting because its emphasis on high performance computing, and it's used by GPU vendors to work on machine learning models. And from our perspective, it's just a nice, flexible and long-term option for storing data in object storage.
Could we try and do an experiment? Like, let's imagine that we've got some data, right? Like a first name and a surname or something. And somebody writes that, they ingest it into Arrow. Could we go through the life cycle of that bit of data? I think it might be useful to enumerate some of the advantages, right? In terms of, the sympathetic, the way it's stored in memory, and the way that you can then process it, like get it back and process it. Does anyone sort of fancy a stab at that, just to illuminate the advantages of using Apache Arrow?
Well, so I could answer that to some extent, but I'm going to try to answer it without talking directly to what XTDB does, because XTDB is a kind of an HTAP, OLTP, OLAP database, which both has to accumulate. Normally, when you work with these kind of files, you kind of assume that file already exists and is some kind of chunk size and it sits immutable on some objects. So Apache Arrow is not different. It has the streaming format, but it's essentially something you assume is going to be mutable sitting around. But you can also incrementally build it up in memory, which is what we do in the new version of XTDB. But untying it from XTDB itself, what you would do is you would write these Apache Arrow files. So there's a streaming format and there's a file format, but not to go into the exact benefit of file format. It's easy to navigate around. So Apache Arrow files, as are Parquet files for that matter, structuring is kind of like sub blocks. So you kind of like a file may have many blocks inside it, and you do the processing in the block. What we usually call a chunk is the kind of entire file, and then you have small blocks inside that. When I say small, that may still be kind of thousands of rows or something. But what you said with first name and last name, so you actually in a way have a kind of a mix in Apache Arrow, as in Parquet for that matter, is that you're storing first names columnar, right? Like every first name is after each other in one array, and every last name is after each other in one array. But those arrays are then stored on a block basis, so you will still have some kind of data locality between first 1,000 first and last names. You wouldn't have to go read the entire file and then go find like the last name if you want to. So it's kind of like a balance between these two worlds. But in general, the idea is that if you come back to XT again, that We store each column in its own file. And if you ingest the document, which may have like hundreds of columns in it or hundreds of attributes, which would look like at the point of ingest, which is actually a document or a row in a table. When you do the query, you may only actually want to see 3 or 4 of those, right? You wouldn't necessarily want to see all of them. So that's where columnar really comes into its own in combination with storage versus compute, because you can actually then just pull down like a very small subset. On the flip side of that, of course, obviously in engineering, there's always trade-offs. If you for some reason need to access all of the data and want to do very wide projections out, you will have to kind of stitch all that data back together into kind of a row format. Because usually what the end user want to see is the kind of like rows and not the columns.
Is that also, Håkon, that if you're doing a join across a number of columns before you do projections, that allows you to do your joins with a respective speed up before you then have to go and dive into the different rows?
Yeah, so essentially, so you have something called late materialization. So you could, in theory, process most of the query until you actually project out the columns, which are more just along for the ride, so to speak. Like they don't necessarily participate in the joins or in the predicates or anything else. Like they just travel along, and you want to project them out at the end when you have figured out what the actual result of the query is. But you wouldn't necessarily want to pay the cost of prematurely materialize all those values in memory. So that's also one nice benefit with this structure. But that itself does not fundamentally come from Arrow. Like it's more like of a usage. Arrow is more of an enabling format for columnar processing. But the main difference for us, why we're using Arrow instead of Parquet, you could argue Parquet is kind of like the gold de facto standard for all these data lakes and all these people working in this space. But because we are a database, you want to have a Parquet, you still need to deserialize it. Even though it's a kind of efficient format, you need to deserialize it. And also the main reasons, because we are kind of want to have this kind of dynamic document, semi-structured data world in our XTDB world, we kind of need the support Apache Arrow gives us when it comes to union data types. So while we kind of ingest arbitrary documents like JSON or richer types, we are actually always storing them in a very strictly typed Arrow. So we know exactly what type every field is, like whatever value is rather. Jeremy said earlier, like if you had used Apache Parquet, you would actually have to kind of duplicate the columns almost, because if someone suddenly decides this first name is not going to be like just a string, it's going to be some substruct or some subdocument, then you cannot store that in the same column anymore. But we can do this. Like there's more cost to this, right? Like there's some overhead every time you get these kind of polymorphic columns, but at least it's possible. And it's like the entire architecture and the design of this format allows for this. It's a very good lingua franca, I think, to actually send data around. It's not just JSON, and it's not something super strict, which because it allows you to do dynamic typing to some extent.
So I guess let's enumerate what are the things that are happening today, what are the trends, and what are the advantages of this separation? Because obviously there are some programmer complexity advantages, just having files on disk and not having to go through an Oracle database or something. There's, every time you go through a product to access data, you're going to be burning CPU cycles. So the most efficient route to the data is directly onto the file system. So combining that with the file formats themselves like Parquet and, in-memory formats like Arrow, which you could sort of argue are performance benefits in that they're mechanically sympathetic to this new CPU architectures and so on. So there's definitely a performance increase. But what are the other trends that we see that is driving this separation, and what are the advantages?
So I think from a long-term perspective, we're really seeing the tail end of Moore's law, the performance of single node compute, price performance of single node compute. So what that means is that scaling compute over data is actually increasingly, you have to move to multiple machines, because yes, you can have lots of cores on the same machine, but those cores aren't getting any faster. But network bandwidth and hard disk bandwidth is increasing. So sort of the physics of the systems that we can build with today's hardware have fundamentally changed from where databases were 20 years ago, and all the context that databases were being developed in 20 years ago. So that's why all modern databases really are chasing this separation of storage and compute, particularly when they have to deal with large amounts of data. There's a certain sort of inertia there, but I think it's also fair to say without the economic dynamics of the cloud, a lot of this wouldn't really even be that feasible anyway, because it's not until you have a highly resilient object storage layer that you can rely on, or use a transactional queue, until you have these cloudy components, which in years gone by would have been operated by the same team as the people running the database. Now they can be run by separate teams or by separate organizations at a much lower cost than the cost of maintaining like a big monolithic database on a set of very expensive compute nodes. So I think, yeah, there's arguments there about cost from a total ownership. Like long-term storage of data, especially if you're not using all of that data all the time. You've got the availability of the data, transactional guarantees, the fact it can be distributed across multiple availability zones. All these things would be unthinkable in, on-premise data centers 20 years ago, trying to run Postgres or Oracle for anywhere near the same budget. And then the scalability, not in raw compute terms, but also multiple engineers working with the same data sets, being able to collaborate within and across organizations. So I think there's quite a few dimensions to chop this up. And there was actually a really great blog post a couple of years ago by a guy called Adam Storm on separating storage and compute. And I'd like to defer to that as the expert opinion on why this is an inevitable trend, not just within the database industry itself, but also anyone working with data systems. Everyone building anything is seeing the same pattern emerging.
Yes, to reinforce that point, it's great that the data is in some open format, so you can install lots of it in the cloud, then separating out the storage from compute, so you can compute against that data in lots of different ways. But it means that anyone can then go to that storage and potentially compute it in a certain way. So it makes it much more open, right? It's not stored in some proprietary database format. It's kind of open for everyone to go and use. I'm sure there'll be some ways that the data is laid out that means it's inefficient to compute it in one particular style. But having it there more open avoids that lock-in.
I think there's a point Jeremy made about bandwidth increasing, in that nowadays you can ship blocks of data and people use S3, and that's obviously part of the trend, is these infinite elastic object stores. But the ability to move vast amounts of data was certainly not so possible on networks back in the day, where we were kind of looking to move compute to the storage because it was very expensive to move big data around. So you were trying to move and get compute ever closer to the local disks, so you would avoid network bottlenecks. But it's funny how the economics have changed to the extent that there's obviously more groups who are making use of the data. So there's data science groups making use of collaborating on data sets. There's machine learning models being created. If you make the data set available, people can do things that they weren't previously able to do. I think in the old days, I guess, you would produce a crystal reports thing on your database and you would ship it out to people in an email. That would be pretty much it. Now it's much more kind of, here's the data, go and play, go and do what you need to do. You might even have traders on the trading floor who are doing extremely sophisticated analytical processing on raw data in order to find opportunities for trading. And that, rather than being subjected to kind of a bottleneck, slaves to being just users of applications that were provided for by IT, now it's a freer world where people can grab the data at source, the raw data, instead of building these ever more sophisticated pipelines of munging data and seeing data fidelity loss, so going from CSV to XML back to CSV into another database, all this kind of data pipelines. It seems there's enormous benefits of going straight to the raw data again and then seeing what people do with it.
I guess the cloud makes it much easier for that data to be fluid. Like storage and memory is so cheap now. And as you said, Malcolm, bandwidth is so much more available that you can stream data into cache stores and you can really move the data to where it's needed. So it's not just this idea that it has to be in like some object store, some S3 type storage somewhere, because like it's so open, you can just really push it and use it where it's needed, which gives lots of possibilities.
So you have a kind of trend of the general separating storage versus compute in the more data lake, data sciences, which is good, right? You have all this data. Well, we can do all the processing you want in some place. You have all these modern kind of OLAP tools, which are like Druid and Trino and these things, which are kind of more operating against existing store and provide a SQL engine on some, but they're not transactional, right? Like they just sit and allow you to access vast amounts of data which already sits around somewhere, and you have a bunch of different kind of plugins to access it or ingest it into these systems. So there's like Apache Kudu and Ignite. There's a bunch of these, right? So you have that, and then you have the traditional database, which are still by design often kind of in a shard model when they're trying to scale up. Like that's how they are been designed from the beginning. So that's the kind of main option they have to scale up. Then you have another category which you start seeing more and more, which is kind of like the closed source or the kind of, I guess, source available and modern new SQL database, which are usually like software as a service or provided by some kind of cloud vendor. So you have that space. They know their own space. They know what they're doing on their own clouds, and they kind of building up something proprietary that you can potentially use. You can get some of the benefits of this, but then you have to jump into bed with this thing, right? Like, or buy this thing. So I think, and I hope we're going to see this next level of actually open source HTAP database, which tries to tie all these things together, which I think we're starting seeing a little bit coming now. And you have several which are open source, but they are usually also more source available things. Because the data lake and the kind of data science world only takes you so far. Like if you want to get the full benefit to some extent of this and how to actually tie all these things together. yeah, that's just a reflection, see if that actually comes to forth. Or we're going to jump from like the old database vendors and most people are going to get built into some cloud vendor or somewhere, right, with all their stuff, but they have no idea how they could actually get that data or the same performance in some other context or same capabilities without being totally embedded with this thing.
It's just the same shit, a different place.
I think we haven't touched on, but it is a whole part of the conversation, is that spectrum from when you're developing something greenfield, the data doesn't exist yet. So you want to put a system in place which can grow and scale with, say, how a new team is building and capturing data and managing it and presenting it through an application interface. So you've got that on the one hand. And the other hand, you've got these people that have a petabyte of data and they need faster and more flexible ways of querying it. And I think what we're saying is, yeah, we can ideally straddle both camps and provide tools which appeal to all people. And I think Arrow sort of makes this promise as well. What is also interesting is that both camps seem to really value transactionality because, of course, people want consistent applications. And also, when you're doing data analysis and machine learning, you still want to know that the version of the data set is correct and that you have the lineage properly tracked and understood, could be even for compliance reasons. So having consistent snapshots over your data lake is seemingly a very important requirement. And not all data lakes even provide that today. So yeah, I wonder if we should touch on that a little bit more. There are some formats that sit on top of things like Apache Parquet, which manage transactional snapshotting of indexes and that sort of understanding which files have which data. So the standards like Apache Iceberg and other vendors have sort of competing tools in this space as well. I think there's Apache Hudi from the Uber development organization. So that, yeah, there's quite a spectrum of people that are interested in the same tooling. And I think everyone just wants the simplest possible thing. No one wants to run a database cluster or run a Postgres node or EC2 nodes running Postgres. They would much prefer to have something which scales with the demands of the application.
Can we try and replay that back? So what you're saying is that you're in this world where we've separated storage from compute. We've got Parquet or we've got Arrow or something. We've got chunks of data inside an object store. But then what users want is a way to have that easy transactional capability to be able to make these real-time updates. And then I think where you're going with that is that's what this modern set of tools will help you to do, like Iceberg, etc. Is that a fair sort of paraphrasing back?
Yeah, it's not necessarily about sort of small updates. It could be, I want to add this huge, multi-gigabyte data set to merge this big CSV import into my existing data set, but I want to do it in a transactional way so that any queries operating on the old version are completely guaranteed to never see anything that's sort of partially in the data lake, or anything that's working on the new version always sees that new version. It never accidentally sees the old, staled cached version. So sort of managing how multiple consumers of this data lake type system can confidently work with that data.
Yeah. So how do we do that then? Because we're building a database of sorts. Is this where we use transaction time to give that consistency? So users can always say, I want to get the data as of this particular transaction time and have a guarantee that it will always be consistent.
Yeah, I think that's always been our position ever since first learning about how Clojure works with its model of time. You want this epochal model where time moves from one consistent state to another consistent state atomically. And that's what transaction time gives you. And that's what we certainly are carrying forward in the upcoming architecture. So transaction time is a consistent point of reference for a given data set. But of course, if you're comparing across data sets, maybe you have like a vector of transaction time because each sort of bounded context may have its own transaction time.
Yeah, I mean, the way I would put it, it's very important to bring time into the equation. I just say everything's easier when things aren't moving. Your kids are easier to get to bed when they're not jumping up and down. And the problem with scalability is made much, much easier when you are dealing with queries and databases, very still data. There's nothing changing. And then you can scale out because that's reasonably trivial compared to the problem where everything is moving all the time. New data's coming in, being ingested. And what we're saying is it's fine to have separation of storage and compute, or separation of data and code, to put it in our language. But, the real trick is separation of storage and compute and time, and keeping all those things separate so that you can still run and scale large queries against data at rest. But actually, you can fool the analytics into kind of behaving and scaling out as if it's at rest, but actually everything is moving and you're still able to cope with the problem of moving data sets. So I think that's what we're hoping to bring to the party, is this additional kind of dimension of time and being able to control time as part of the equation.
So I was considering taking a small step back here and look at these more data lake, bring some consistency and structure to your data lake, like Iceberg or Delta Lake, and these kind of tools usually work in quite chunky, large transactions, but they consistently give you some understanding. If you look from the other side, where you can start from more, then you start in the kind of data lake OLAP space. If you start in the OLTP space, you come more into the HTAP in-memory database, these kind of things where you still want the latency of the old TD database, but you want to have the benefits of the storage versus compute model. So you're kind of trying to solve it in a slightly different way. There are a lot of overlap in the technologies involved, or at least the names of the technologies involved, but the way you do it is slightly different, right? Like you could say storage versus compute and the object store, like on databases without really having database nodes, would be kind of been a solved problem if you hadn't had this kind of latency gap and someone needs to manage the transactionality like in a low latency way. That's why you still can't really get rid of the kind of concept of database nodes per se, right? Even if they are transient in the storage versus compute world and they come and go quite easily, but you still need someone to manage these transactions for you. And basically bridging that gap, or rather making this gap as small as possible, I guess is what we're going to start seeing over the next few years. In a way, you want to get rid of the trade-off. You don't want to have any extract, transform, load jobs. You don't want to have separate databases all over the place. You want to be able to run an easy way to access everything and do any kind of processing. So one nice thing, of course, with storage versus compute is like assuming you have the data there, it's easy for you to fire up some kind of OLAP nodes, do some advanced things that your DBA would not allow you to do on your production cluster normally, right? But you can just fire up your own nodes and access the same data. But these nodes won't necessarily be up to date in the simple case, right? If you say these are not actually transacting anything or have any knowledge about what's currently happening, they're always going to be lagging behind. So this gap, closing this gap, I would argue is probably what we're going to try to see. And it's one of the things that XTDB tries to do. It's not just a data lake kind of OLAP tool, like it is something that tries to bridge this gap. But doing that is non-trivial. Like, and obviously coming back from XTDB 1, not strictly Kafka, but having some form of deterministic log and decoupling transaction submission from transaction processing is the key to the way we're going to try to achieve this even in XTDB 2. But it still doesn't really solve because you need some way to fast append in the new transactions, but you also want to kind of slightly slower store. Like it's not called iceberg for nothing, right? You want to have something which is slightly larger and slower where you store the data at rest eventually. So bridging that gap, you essentially has to write ahead log in a big way. So there's this nice paper on the S3 as a database, which is one of the original early kind of like the cloud is new, how to use S3 as a database, like how do you build a database on top of S3 itself. This was before Amazon had like hundreds of different strange acronyms in their family, right? Like there was a few things you could keep in your head. But anyway, I think it's important to not get sucked into the cloud vendors, world. Like you want to have an abstraction of a few simple things. They're going to provide a lot of good stuff for you. But one thing you don't want to provide is lock-in, right? So you're going to try to rely on as little as possible, but still get the benefits of what they can provide, like object storage, some form of queuing for the actual transaction themselves. And then we can try to marry them up in a simple way as possible, but it's not necessarily super simple.
Cool. I want to pitch to you guys. This is just a sort of wrap up, really, a bit of a fun thing at the end. But do you think that separating storage from compute is a bit like what we don't like about OO? Like with OO, you've got like classes and data, all encapsulated within this one weird object thing. Is separate storage from compute the idea of moving to more of a functional programming model where you've got the data and the functions and they're separate things, but in the large, it's the same kind of pattern that we're scaling up and scaling simplicity of this and taking it out to a broader level?
So I'm going to say one thing, but let someone else speak. But one thing we haven't talked about so far is lambdas and things like function as a service things, which like the extreme end of these separate storage from compute systems and databases. You essentially have you don't actually have nodes. You have lambdas sitting around doing. But again, because of the essentially bottlenecks and reality of things, it's hard to do the full-on transactional processing properly in those kind of lambda systems. It's probably possible if you really try, right? And I've seen some papers around trying to do that. But it's like, I guess that would be the kind of extreme end of what you're saying, right? You have functions and you have data which sits in the object store somewhere.
That's the end game, is what you're saying. Just have like these functions in the cloud that can access this data, whim, and then do what they want with them.
Yeah, again, if it hadn't been for this latency of having to process transactions, actually storing them in some kind of efficient fashion in the object store, you would essentially be there already, but you're not. There's another problem with this is the caching itself, but you can potentially solve that with like tiered caching models. These nodes, right, in the separate storage for compute databases, they are kind of transient and they can be killed and they can come back. They can easily spin up, but they also do accumulate, often caching and copies of all these chunks. You don't have to start cold. So even if bandwidth is fast, you don't necessarily want to go entirely cold all the time after the object store every first time you get the query. These things are still a bit hard to solve in the function as service. It makes sense, right? As you say, it's kind of like the functional program model. Like it would make sense to try that, right? But my feeling is that we're not 100% there yet. We're making this leap now, trying to get kind of like HTTP processing in the storage versus compute space. And that's potentially it's going to be a small phase, which we're going to cross over to full on.
I think for our listeners, actually, could you just define what you mean by HTAP? What is HTAP?
Yeah, it's hybrid transactional analytic processing. So normally these worlds are separated, right? Like not separate as storage versus compute, but they're separate in the sense that you have online transactional processing where you do your real work and then you shift over the data to either a data lake, some data warehouse, whatever you want to call it, where you have like there's some latency between this data, and often it may be rolled up, or like it may actually be not compressed like that, but may actually be aggregated somehow. So it may not be the raw data. On there you can do your analytics. But it's kind of like a model which mainly is there because you don't necessarily want to confuse or keep all the data around in the old P cluster or old P system. If that has to be a very, very fast system with fast disks, it's like you don't necessarily want to do that. We start to talk about transaction time and stuff, but in the temporal database world, this world in a way kind of vanishes because you kind of want all data around anywhere all the time, but it didn't used to be very practical. But that's also something storage versus compute actually allows. It's not necessarily a tax or even harder to keep all the data around. It's kind of the side effect of the design itself.
Great. I think we made some headway in understanding what we mean by the separation of storage from compute. It's been a good intro to the subject. We're doing lots of thinking and reading and understanding and coding against this. So no doubt we'll visit it again in the future. I just want to say thanks to everybody on the call and go forward and enjoy separating storage out from compute.